Well, hello everybody. My name is Nadhifa Sofia, and today I'm gonna present to you all about my big data analysis assignment, which is about Kafka. First and foremost, we need to know about the Kafka. The Kafka introduction will be explained by me. The Kafka architecture system will be revealed just like this. For example, this is the machine learning application production architecture. We got here the Kafka Connect, which is database and applications are the Kafka input, and we store the feature data input into our message broker called Kafka by using Kafka producer, which uses a language programming language just like Go and then Net, Python, and etc. And when we want to register our schema, we need to define the schema registry first. The Kafka input, or maybe our applications and database, are processed by REST proxy. And then from our message broker, we can produce our machine learning application by using Kafka streams. And then the Apache Kafka also uh, allow us to train our data, and then we got the model built-in. And if we are not satisfied with our model, we can uh, adjust our model parameters by using the Apache Kafka itself. Apache Kafka is a distributed streaming platform. Apache Kafka is used for microservices terminology, and then some sort of things in backend. A streaming platform has three key capabilities. First, publish and subscribe to streams of records, similar to a message queue or enterprise messaging system. And then it can store streams of records in a fault-tolerant, durable way, and also process streams of records as they occur. Kafka is generally used for two broad classes applications, just like building real-time streaming data pipelines that reliably get data between systems or applications. Also, building real-time streaming applications that transform or react to the streams of data. And we got the question why we need to use the Apache Kafka. First, it is created by LinkedIn and now is open source project mainly maintained by Confluent. And then Apache Kafka is distributed, resilient architecture and also fault tolerant. The Apache Kafka also has horizontal scalability. Let's define the term vertical scalability first. For instance, we have a traditional database server which is starting to get overloaded, and then the way to get this solved is to simply increase the resources just like CPU, RAM, or SSD on the server. This is called vertical scaling, where we add more resources to the machine. There are two big disadvantages to scaling upwards. First, there are limits defined by the hardware, and then we cannot scale upwards indefinitely. And it usually requires downtime, sometimes something which big corporations cannot afford. And then horizontal scalability itself. Horizontal scalability is solving the same problem by throwing more machines at it. Adding a new machine doesn't require downtime, nor are there any limits to the amount of machines you can have in your cluster. The catch is that Not all systems support horizontal scalability as they are not designed to work in a cluster, and those that are usually more complex to work with, just like this one. We got the graph with X is the extra capacity needed, and then the Y is price per capacity unit. And the horizontal scalability becomes much more efficient after a certain of point. And then the vertical scalability costs rise sharply after a certain point. This is the horizontal scalability, this is the vertical scalability. And the initial costs associated with horizontal scalability tend to be higher. And also Apache Kafka is high performance. Its latency is less than 10 milliseconds with the real-time message streaming. Real, yeah. And then Apache Kafka is used by 2,000 firms, 35% of the Fortune 500. Well, there are so many Kafka use cases. First, Kafka can be a messaging system, and then it can also be of activity tracking. It can gather metrics from many different locations, and then application logs gathering, stream processing with the Kafka Streams API or Spark, for example, decoupling of system dependencies and integration with Spark, Flink, Storm, Hadoop, and many other big data technologies. Well, this is the Kafka's examples. It's like Netflix use Kafka to apply recommendations in real time while you're watching TV shows, and then Uber use Kafka to gather user, taxi, and trip data in real time to compute and forecast demand and compute search pricing in real time. Also, LinkedIn use Kafka to prevent spam, collect user interactions to make better connection recommendations in real time. And remember, Kafka is only used as a transportation mechanism. For example, in microservices, decoupling of data streams and systems. Well, Apache Kafka is a distributed streaming platform capable of handling trillions of events a day. It provides low latency, high throughput, fault tolerant publish and subscribe pipelines, and is able to process streams of events. And in this architecture design, we assume that this is the core, the Apache Kafka, and then there are many cluster in this Apache Kafka, which also stream the data from this one, from this cluster into this one, from this cluster into the other one. If we connect uh, one cluster, it will connect to all of the clusters um, along the core. And this terminology is used in microservices. Apache Kafka has uh, some core APIs. First, producer API. Applications can publish a stream of records to one or more Kafka topics, and then the consumer API. Applications can subscribe to topics and process the stream of records produced to them. And the third is Streams API. Applications can act as a stream processor, as consuming an input stream from one or more topics and producing an output stream to one or more output topics, effectively transforming the input streams to output streams. And the last connector API is to build and run reusable producers and and or consumers that connect Kafka topics to existing applications or data systems. For example, a connector to a relational database might capture every change to a table. And then what is stream? Okay, well, Kafka consists of records, topics, consumers, producers, brokers, logs, partitions, and clusters. Records can have key, just like which is optional, value, and timestamp. Kafka records are immutable, which we got here. We assume that this is the Kafka records. And if we think a topic as a feed name, a topic has a log which is the topic storage on disk. And then a topic log is broken up into partitions and segments. The Kafka producer API is used to produce streams of data records, and then the Kafka consumer API is used to consume a stream of records from Kafka. And then a broker is a Kafka server that runs in a Kafka cluster. Kafka brokers form a cluster, and then the Kafka cluster consists of many Kafka brokers on many servers. Brokers sometimes refer to more a logical system or as Kafka as a whole. Well, stream is unbounded, continuous, real-time flow of records. We don't need to explicitly request new records, we just receive them. Then records itself are the key value pairs, just like this. This is we call records. Groups of record we combine into stream. Stream is easy data processing and transformation library within the Kafka. With Kafka streams, we can transform the data, enrich the data, detect the fraud, and then monitoring and alerting. Kafka Streams has a standard Java application and it doesn't need to create a separate cluster, highly scalable, elastic, and fault tolerant, exactly one's capabilities and one record at a time processing. We got here the Kafka Streams architecture design. First, we got the Kafka sources, and then we can save it into Kafka into the connect cluster workers, and we after that we save it into the Kafka cluster, which is separated by some brokers, and then it will goes it will go into the first stream application. It will stream into first application, the second application, and then the third application. After we transform and process the data, we can produce our data into the connect cluster workers, and then it will be saved or revealed in sinks as an output. Kafka Core's ecosystem. Well, Kafka Core has source systems, and then from the source systems or the input, we can use the Kafka producers API, and then we got here the Kafka with the zookeeper on it. The zookeeper is a distributed key value store. It is highly optimized for reads, but writes are slower. It is optimally used for reading, not for writing. It is most commonly used to store metadata and handle the mechanics of clustering. And Zookeeper is used for storing all sort of metadata to mention some, just like consumer groups offset per partition, ACL access control list, and producer and consumer quotas, and partitions leaders and their help. After that, we connect into Kafka Consumers API and we got the target systems. For the extended API, first we got the Kafka input, as known as the source systems, and we stream into Kafka Connect source, which has the Kafka streams, and then the Kafka cluster 1 will be replicated by using mirror maker into the Kafka cluster 2, so they will have so many clusters on it. And also we got the Kafka Connect sync, and we can produce our target systems here. This is the Confluent component schema registry and REST proxy. Well, we got the Kafka input. For example, this is the Java producers. And when the Java producers wanted it to stream the data into the Java consumers, it should register the schema by using Kafka schema registry, and then after the producers and consumers is connected, will be a Kafka cluster is created, and then after that we can use the Kafka REST proxy, which is this is the get endpoint to fetch all of the data from non-Java consumers, and then this is the post endpoint to store all of the data from non-Java producers into the Kafka REST proxy. And Kafka in enterprise architecture. Well, basically, Kafka has two pipelines, just like this, the real-time one and then the batch one, or the asynchronous one. Kafka input, just like applications, and then website, financial systems, email, customer data, and then also databases will be saved into Kafka temporarily. And then we will analyze analyze the by using the big data technology, by using Spark or Storm or Flink, and it will produce just like real-time analysis, dashboards, and applications or consumers. For the batch or asynchronous system, the data from Kafka will be uh, distributed into Hadoop, Amazon, and RDBM as relational database management system. And this will produce the data science, reporting, audit, backup, or long-term storage. In advance, I said that Kafka is consistent of topics and partitions. Well, topics is a particular stream of data, just like this. This is a topic. Topic is similar to a table in a database without all the constraints. We can have as many topics as we want, and then a topic is identified by its name. And topics are split in partitions, just like this. Each partition is ordered from the partition 0, partition 1, partition 2. Each message within the partition gets an incremental ID called offset. This is the offset 0, offset 1, offset 3, offset 2, and then etc. Offset only have a meaning for a specific partition. For example, offset 3 in partition 0 doesn't represent the same data as offset 3 in partition 1. This thing will not be same as this thing. And then order is guaranteed only within a partition, not across partitions. After that, data is kept only for a limited time. As said before, this is the temporary data, and the default is 2 weeks. After 2 weeks, the data will be changed. Once the data is written to a partition, it cannot be changed until 2 weeks because uh, Kafka is Kafka data is immutable has immutability characteristic, and then that data is assigned randomly to a partition unless a key is provided, and then we can have as many partitions per topic as we want.